Welcome everyone to today's Explainer. I am absolutely thrilled to have you here for this lecture. Look, we're going to be unpacking a topic that completely captures the imagination of travelers and city planners alike, but honestly, it's surprisingly misunderstood. We're talking about the fascinating realities and, yeah, the harsh limitations that keep bullet trains from just being built everywhere. Because, we all love the idea of zipping between cities at lightning speed, right? But as you'll see, there are massive economic and geographic forces standing in the way. So, let's just get right into it.
Okay, let's dive right into our syllabus for today's Explainer. We've got 6 key modules to unpack. We'll start with the high-speed reality, move into social and economic costs, then the urban transit dependency, battling the geography, steel wheels versus maglev, and finally wrap it up with the ultimate trade-off.
All right, Module 1, the high-speed reality, speed versus reach. This right here is the fundamental compromise at the very heart of high-speed rail.
You see, incredible speed isn't a free pass. It requires highly specific, dedicated routes. High-speed rail really only suits densely populated intercity corridors. And that brings us to a huge social drawback. It inherently leaves medium and small towns completely behind. If you don't happen to live in a major booming population hub, well, you simply don't get the direct benefit of that blazing fast connectivity. Prioritizing that mind-boggling speed between massive cities inevitably leaves smaller communities in the dust.
But it doesn't have to be completely exclusionary. Japan's famous bullet train timetable actually illustrates a really brilliant workaround. What they do is balance lightning-fast, non-stop services that shoot directly between the megacities right alongside slower services on that exact same network that actually take the time to stop at the smaller stations. It's a fantastic, real-world example of using smart scheduling to mitigate that social drawback and really extend the reach of the infrastructure.
Moving on to Module 2, social and economic costs, or as I like to call it, the price of speed. Now we have to address the elephant in the room. Let's be totally blunt here. The primary objection to high-speed rail anywhere in the world is always the cost. These systems are, to put it simply, phenomenally expensive. We're not just talking about laying down some new tracks, it is an entirely new, incredibly complex class of infrastructure. That sheer eye-watering expense is the single biggest roadblock for almost any high-speed rail proposal out there.
And this leads to a crucial point. Who actually pays for it? Because those initial construction costs are so incredibly high, the private sector is almost entirely unwilling to touch these projects. Private companies just do not want to take on that kind of enormous, risky financial burden. So what does that mean for us? It means the burden inevitably falls on taxpayer funds. Public money literally has to be used to get these massive networks off the ground.
Which brings us to Module 3, the urban transit dependency, the last mile problem.
Now, you might think a bullet train solves all your transit problems, right? Well, not exactly. Think about your actual door-to-door journey. People don't just magically teleport to the city center. Step 1 is usually taking a local metro or a connecting train just to get to the high-speed hub. Step 2 is that blazing intercity high-speed rail segment. And then step 3, once you arrive, you have to jump onto a local light rail or transit system to actually reach your final destination. The high-speed part is completely sandwiched between and totally dependent on local transit at both ends.
Our source material sums this up perfectly, stating, in order to work effectively, high-speed rail must be backed up by a decent urban/light rail transit system. It's like a giant puzzle, and the bullet train is just one piece. If a city doesn't already have great local public transit, dropping a multi-billion-dollar train station right in the middle of it isn't going to magically get people from their door to their office.
All right, let's shift gears to Module 4, Battling the Geography. Subtitle here is Earth's Resistance.
Constructing these tracks is literally a battle between human engineering and the natural landscape. High-speed lines have a very strict physical rule. They absolutely must be as straight and as level as physically possible. To force that straight level line right through the countryside, you have to make massive landscape alterations. We're talking huge embankments, giant viaducts, deep cuttings, and enormous tunnels. It is incredibly difficult and wildly expensive to wrestle the Earth into submission like that.
And the engineering challenges get even more surprising. For example, mountain tunnels aren't always a perfect fix. Pushing a high-speed train through a tight space can actually create serious, dangerous wind turbulence problems. Oh, and spanning vast bodies of water, that is a total rarity. You naturally cannot just build high-speed railways over water for long distances. Mother Nature really puts up a serious fight here.
Okay,
Module 5, Steel Wheels versus Maglev, the physics limit. Now, what's really interesting about this section is how we literally hit the limits of physics.
Let's contrast the two dominant rail technologies. On one side, we have the traditional mechanism, steel wheels running on steel rails. On the other, the futuristic maglev, which uses an electromagnetic system to literally hover above the track. Now, maglev can hit unbelievable commercial speeds. We're talking over 500 kilometers per hour. But wait until you hear the drawbacks. Maglev's incredible speeds come with an exorbitant construction cost, huge energy use, and they are incredibly loud during operation. It is massively prohibitive compared to traditional steel.
Which brings us to a critical number you need to remember, 400 kilometers per hour. For a traditional steel-to-steel system, commercial speed normally maxes out right there. Going beyond 400 kilometers per hour with steel wheels is considered highly uneconomical because the maintenance required for the track and the trains just absolutely skyrockets. So 400 kilometers per hour is really the maximum economically viable commercial speed.
And because maglev is so ridiculously expensive and prohibitive, it's actually incredibly rare. There are only a few in commercial operation globally, like the SMT high-speed airport link in Shanghai, the Limino line in Nagoya, and the Incheon Maglev in Korea. And what's crazy is that two of those, the Limino line and the Incheon line, are actually low to medium speed systems. The Incheon one maxes out at just 110 kilometers per hour.
But check this out, 8 minutes. That's a fun fact to show the extreme scale of Shanghai's maglev line. It covers a 30-kilometer stretch, operating at a maximum commercial speed of 430 kilometers per hour, and it completes that entire journey in an astonishing 8 minutes. It's an absolute marvel of engineering, but, as we just learned, an extraordinarily expensive one to operate.
Finally, we arrive at Module 6, the ultimate trade-off. Is it worth it?
We've unpacked the speeds, the massive social drawbacks, the exorbitant public costs, and the fierce geographic constraints. Now, I want you to synthesize all of that. Remember, because the private sector stays away, your public tax dollars are on the hook for these incredibly expensive systems. This raises a really vital question. Could that massive amount of public money be more effectively spent on other transit projects to actually reduce traffic congestion and pollution?
And that brings us to the final exam question for today's lecture, something I really want you to ponder. Is high-speed rail actually the most cost-effective way to gain lower pollution? Look, we all love the dream of zipping across the country at 400 kilometers per hour. But when you factor in the billions in public funds, the required landscape alterations, and the sheer physics of it all, what's the right choice? Thank you so much.